Okay, so this is lecture 3 of our lecture. Let's go to our previous lecture content. So at the end of our previous lecture, we have thought about how can we identify the velocity and inverse mass of an electronic state. So we assume that by some means we can calculate the relation between energy versus a wave vector. So this is of course energy, and this is wave vector, and you know that this wave vector or wave vector is corresponding to an electronic state. So once we know the relation between this energy and wave vector, then from that one we can calculate very important properties like velocity and inverse mass. So calculation can be done quite easily. For example, this is the expression for group velocity. So you know the energy as a function of three-dimensional k vector and take the gradient over this energy function, then you will get certain vector, and you know this is corresponding to or proportional to the group velocity. And inverse mass, actually inverse mass is a tensor. It can depends on two different directions. So here you have I and j. These should be interpreted as x, y, or z, the directional component. Once we have a certain direction, then we can take the second derivative with respect to ki and kj respectively. Then you will get the value for this component of inverse mass tensor. For example, let's have a look at the silicon conduction band. So here you are looking at an expression for silicon conduction band, and where can you find this EC? So let me just highlight it here. Yes, so sorry about that, I can see clearly. So here we have a gamma point, and here we have a X point. X point is the zone boundary, first Brillouin zone boundary, where our principal axis kx and ky and kg meet the boundary. So we can find 6 copies of this X point. For example, starting from this gamma, so you can find this is a certain X point, and there is another X point. So please try to identify another X point, and if we go to in this direction, then you can expect that there exists another one, and also maybe somewhere there we will have another one, and finally we will have the 6th one. So now we can imagine a one-dimensional coordinate starting from our gamma and ends at our point x, and you know that where can you find this conduction band minimum? So you can find it. So if this is measured as length 1, then you can find it at approximately 0.85. So please try to visualize it. Then if we visualize it with a certain different color, then maybe there is somewhere here. And if this is the length 1, and maybe you have somewhere here the minimum point for your conduction band. So you have 6 different copies of it. So therefore, although we are now saying that silicon conduction band follows this kind of form shown here, it means that there are 6 copies of this kind of thing. And you know that this K is originated or translated to the minimum of each value. So k, for example, can be sometimes can be a vector nearby 0.85, 0, or of course the scale is the length between gamma and x point. Okay, so this is corresponding to 2 pi over a. This is the distance between gamma and x point, and around 0.85, and of course we can say that there can be plus minus, or sometimes we can have a plus minus 0.85, or sometimes a plus minus 0.85. There we can find different minimum values of our silicon conduction band. So please note that once again, what is actually this k? So this k, for example, for x value, this is nothing but our original kx, ky, and kz minus our minimum value. So therefore, for example, for positive x value, we can say that 0.85, 0, that is written as this k value, so local coordinate. And of course, in this case, if k equal to 0, when we say that now k equal to 0, that means that our k point is exactly corresponding to the minimum point of 6 different values. So the energy will be exactly the conduction band minimum value, so that will just vanish. And here you have some expression for these 6 different values. By the way, maybe to some of you the term like belly seems to be a little bit strange. So we are now saying that belly, when we say belly, then typically we are saying only one copy nearby this point, and nearby this point, and nearby this point. So although we have a conduction band, but it contains 6 different values. Okay, so now we can say there are 6 different values, and each of it is well approximated by this expression. So let me just do some calculation about velocity. So let's say that there exists a certain k value, then please try to calculate the group velocity at a certain point. Then how can you calculate it? First of all, we have to have 1 over half and takes this gradient operation. So x directional component can be obtained by this kx directional partial derivative. So you will have just 2, and you will have mxx to kx. So are you with me? Then of course these 2 numbers are gone, and eventually we will have x directional velocity, which is given by mxx here, and half kx. That will be the x directional velocity. And of course we can calculate the y directional component. Then for y directional we have to take the partial derivative with respect to ky, and that will give you once again, so squared half over 2 my 2 ky. So you will have y direction, your y directional velocity is simply given by ky divided by my. So it is quite easy to imagine like this. So now once you have a certain k value, then half times your k vector can be regarded as a certain momentum, and for each direction you take the directional mass mxx and or myy or mzz. So that will be the expression for your group velocity. Okay, mzz. So that will be the form for your group velocity. And how about this inverse mass instead of this velocity? Then you can take the second derivative. Let's do it together with me. So how about the second derivative of our energy with respect to kx direction? Then you will find that when you take the second order derivative, then this one just yields number 2. So we will have just 2mxx, and these are also vanishing. So we will have this kind of result. Of course, if we take the partial derivative not for kx but for example ky, then you will have myy and myy here. So simply speaking, when you take the partial derivative of your energy with respect to certain k direction, then you will have the numbers like half square divided by your directional mass, and you know your inverse mass is given by the second order derivative normalized by your squared half bar. So then my question is, what is your x directional inverse mass? Then you will find that this is just 1 over mxx. Oh, you may say that, okay, this is just identity, but please note that in the left hand side I just written this expression as a component of your inverse mass tensor, and the right hand side you have a certain scalar number, x directional scalar number used in this specific expression. So anyway, once we have ek relation, then following this simple manipulation, takes the first order derivative or takes the second order derivative, you can find very important two quantities. What are they? They are the group velocity and inverse mass. That will determine the transport property of our certain electronic state. Okay, so that is just to summarize here. So on ellipsoid belly, so you can find on isosurface. So the iso energy surface. So it means that over this surface, this ellipsoid, everywhere you have the same energy. So for example, here you have a certain energy, and that energy value is the same for this one. Although our origin for k value is located here, the distance between this direction and distance along this direction are different, because you know this one has heavy mass and this one has relatively light mass. So please understand, when you visualize an iso energy surface of a certain belly, if you have a certain direction where it is quite much expanded, it means that it is corresponding to heavy mass direction. And if you have a certain direction where distance from the origin of your k is quite short, then that is corresponding to the direction for your mass, effective mass is small. So let me just explain a little bit further. For example, this is the typical drawing. Say that now you have kx, ky, and kg direction. And when we just draw the iso energy surface for each direction, then you can find certain things like this. This one, oh, sorry about my ugly drawing. So there, especially for this guy, their principal axis should be aligned to this ky direction, and this one too. Then let me ask you one question. For this one, what is the direction for its heavy mass? Yes, this is the direction for its heavy mass. And however, for this belly, what is the direction for its heavy mass? Yes, this is the direction for its heavy mass. Let's say that now we have two different electrons occupying the same energy. For example, now we can imagine one electron occupying this point and another electron occupying this point. Since we are considering an iso energy surface, they have the same energy. Then what I wanted to ask you is whether this one has a higher x-directional velocity or this one has a higher x-directional velocity. The answer is when they have the same energy, since this guy has light mass and this one has a heavy mass. Now we can understand this one will contribute heavy mass. So if we are considering certain transport along this x direction, then which one is more beneficial and which one is less beneficial? So you can easily understand, since this guy has light mass, that will give us a fast movement, and this one will be quite bad to carry our charge along this x direction. So now we can think about an application of this understanding. So for example, later we will see that there exists a certain transport direction of our electrons. Typically, for example, you can consider a source of your transistor, and you can think about the drain of your transistor. Typically, your electrons are moving from source to drain direction. In this case, if we have three different pairs of our silicon bellies, then which one is more preferred one for using as a transport channel? So you can easily understand these are preferred channels for our electron movement, and we wanted to actually eliminate the contribution from this heavy mass one. Of course, we have to say that this one and this one and this one, these are all identical, so they have the same direction. For example, this one has heavy mass along this direction, but for that direction, other direction, it has a lighter mass. Although I'm saying that this is good for this x-directional transport, yes. However, if we consider y-directional transport, then this guy becomes quite a bad channel for our electronic transport. So means that we have to introduce certain ways to break this symmetry. So later you will see how can we break this symmetry between three different pairs of silicon conduction bellies. Okay, so anyway, this is a simple expression for our conduction band. In the case of a silicon conduction band, although we have three different belly pairs, but anyway they follows more and less parabolic behavior. What is the parabolic behavior? Energy can be expressed as second order or quadratic function, or I made a sorry about that. I made a typo here. So please, this should be of course z. So I made mistake. So I will correct this typo very soon. So anyway, this is the quadratic function of our silicon k value. However, in the case of holes, I mean that the valence band shows much more complicated behavior than the silicon conduction band, although we have no degeneracy like number of 6. In this case, we have there are 6 ellipsoidal valleys in our silicon conduction band. So if you have any question, then please give me a question. So okay, that was the contents we have not covered in our previous lecture, so I quickly covered the remaining thing. And the main thing we wanted to review in today's lecture is the concept of density of state. So of course I believe that all of you have already the concept of density of states quite well, but let me just review this important concept once again, so please refine your understanding once again. Now let's think about these two different systems. I mean that here we have two different cuboid. So there is 1 and 2, and it has like a length scale Lx, Ly, Lz. So this is a relatively small one, let's say. And now we just magnify it by factor of 2 for each direction. So x directional length is just twice, y directional length is twice, and z directional length becomes also twice. Then please think about now your k space and now your k space. When you have this small box Lx and Ly and Lz, then for example along x direction, then what will happen? So you will have so many different available k values, and each of them will have certain difference like 2 pi over Lx. Okay? So you will have this small one. So please don't be pulled by this one. Maybe some of you will say that okay, no, the difference between these neighboring k points is not given by 2 pi over Lx but 2 pi over a. No, it's not. A is used as a unit cell size, which is quite small, so this 2 pi over a becomes quite a large number. But what I'm saying is, if we have a certain unit cells, many unit cells, and two neighboring k points have different k numbers only by this 2 pi over Lx, which is Lx is much larger than our a values, because a is unit cell length and Lx is our measurable macroscopic length, for example 1 centimeter or 1 micrometer, like or a few 10 nanometers. So this is much larger than that. So this is the difference between these two neighboring k points. Then now let's consider the system which is enlarged by factor of 2 along each direction. Then here once again it has its own k space, and each k point will be differed by only by 2 pi over what? Lx? No, because the x directional size, the system size becomes twice. Now we can say that it will be normalized by 2 times Lx. Simply speaking, so please note that the size of your K point. So let's visit once again our Brilliant zone. Then what is the position of our x point? The x point is simply given by 1, 0, 0 times 2 pi over a. When you have a look at the coordinate of your x point, do you have any dependence on the real system size? For example, if you have enlarged your system size by twice, then do you have any difference in your x coordinate? Actually not, because it is solely a function of unit cell size A, not a function of Lx, Ly, and Lz. Then what happens if we have twice larger point? So in the case of a previous Lx case, then we can say that, now let's say that this is your Brilliant zone boundary. This is a boundary, and here you have x point, and previously your second last point just nearby the boundary value was, the distance was just 2 pi over Lx. However, if you introduce twice larger system, then the distance between your zone boundary value and the most closest one, this guy, becomes just 2 pi over 2 times Lx. Simply speaking, when you have larger system, then you don't have expanded Brilliant zone, but your Brilliant zone is occupied by more densely populated discrete K points. So now you want to have enlarge this cube, then your points will become more close to the zone boundary values and close to continuous domain. Okay. So what is the main message of this constellation? So when we have a certain Lx and Ly, Lz directional lengths, then we wanted to ask what is the volume of a state in the K space. Each K space is separated by 2 pi over Lx along x direction and kx direction, and 2 pi over Ly along ky direction, and 2 pi over Lg along kg direction of volume. The volume of a cuboid in the K space can be simply given by this number. So are you with me? It is just the product between 2 pi over Lx, 2 pi over Ly, and 2 pi over Lz. And if you understand this one, then if we go to twice larger system along each direction, then you can easily find that yes, a volume for our K space is now 8 times smaller than our previous, the original system having Lx, Ly, Lz as its volume. So simply speaking, so this is a typical difficulties when a student try to understand the, starting from the discrete K point to the continuous K space. So that's the reason why I'm emphasizing this concept. So simply speaking, really the size of your electronic states in all case space really depends on the volume. So in general, we can state in general way like this. If you have one point in your system, then in case space it can be regarded as this 2 pi over volume, and this volume is a real space volume of your system. For example, if we consider 1 centimeter by 1 centimeter cube, then that will become just 1 cubic centimeter. Okay, anyway, that is used as a normalization factor. So now, that from this understanding, we can make a simple, really a simple and straightforward observation. If we have certain count for a certain k value, then it can be regarded as just k space integration. However, please note that if we do it, then there introduce a certain change in its unit. Left hand side we just make a sum, and there is no differences in its unit. However, since we are doing the integration always introduce additional dimension with respect to this integration variable. So we have a cube of wave vector introduced. That should be normalized in order to match their dimensions. So how can you do that? Since one electronic state takes this kind of thing, so we can just normalize it by volume over 2 pi over square. Then you can find it. Okay, so now think about this special case. For example, if we wanted to just add 1 or evaluate 1 for every k points, then you can easily understand this is the right way to make the conversion from just discrete summation to the continuous integration. So that is the reason why we have these seemingly quite strange factors like 2 pi over 3 in everywhere in our derivation. Okay, so let me just state once again. Now everybody in this room understand on electronic states occupy the volume like this. One single state have the volume in its k space. So if we have to calculate the number of states inside a certain infinitesimal volume like dxk du, so let's say there is a small volume in our k space, and this is dkx, dky, and dkg. Then our question is, how many electronic states are there? Then that should be calculated by this way. If this volume is corresponding to, for example, 2 pi over cube divided by our volume, then the product will give us just exactly number 1. Simply speaking, if we have the smallest volume we can imagine, then it will give us only 1 unit electronic state inside our k space. And if our considered volume is larger than that, then we have to normalize it, and that will give you certain number how many states are there. So using this one, so we can also number of states inside, not in this just dkx, dky, dkz, but inside an energy range between energy E and energy E plus dE, then it can be obtained by the integration over k-space. However, integration domain is restricted by this energy constraint. When your calculation, when you have your k value, then try to evaluate the energy value, and this energy value is belonging to a range between E and E plus dE, then you can perform this integration. Then that will give you the number of states inside a certain energy range. Now you may feel that this is closely related with the density of state. What is this number? The physical meaning of this one is we have a certain energy level and we have a certain margin for our energy, and how many states are there. It has the unit of number per electron volt. For given energy value, for unit energy value, how many states are located in that system. It can be obtained by this simple integration over our k-space. Okay. And now this one gives us the concept of density of state. So density of states simply means that, okay, this value itself is given by number per electron volt. However, here we have a volume, and this volume is normalized. If we just eliminate this volume, it means that we just multiply or divide this number with volume, then you can find a certain numbers like number of states per electron volt per unit volume or cubic centimeter. That is called as density of states multiplied by our energy difference dE. So you can find that this is corresponding to your equation 2.1. I just repeat how can we derive the concept of density of state from our k-space, and at the time the most important observation is for each electronic state it has a finite volume in k-space. So when you just change the summation to your integration, we have to have this conversion factor 2 pi over something, and this 2 pi over something, here something means that the size of our system, volume of our real space system, real space volume of our system, but that is normalized. So although density of states is sometimes regarded as energy density per electron volt, however it has also volume in it. So if you have three-dimensional space, three-dimensional system, just to we consider right now, we have this kind of thing. However, later you may, if you are working with a two-dimensional material or one-dimensional nano ribbon, then your system is no longer considered as three-dimensional space, three-dimensional system. Sometimes you may think about two-dimensional or one-dimensional system. In this case, your normalization is no longer corresponding to the volume of your system. That really depends on the dimensionality of your system. For example, if you are working with even the silicon MOSFET, not fancy two-dimensional material, but when you just consider state-of-the-art device right now, currently manufactured, then you may find that the actual shape of our channel is no longer can be considered as a three-dimensional one. You know, along this direction, the size is about 5 nanometer, and along this direction, you know, it depends on the situation, but if we have the minimum one, then that will be 5 nanometer, but more realistic, we will have 10 or 20. That will be the reasonable size for this one direction and another direction. Of course, along the third direction, we have a long channel, relatively long, much longer than that. In this case, can you expect the free movement along this direction or that direction? Actually, it's not. If your electron just to move just 10 unit cells, then it will find that it hits the wall between silicon and silicon dioxide. And when it comes back to the opposite direction, and when it moves just once again 10 unit cells, and it will be once again hit by another wall located in its bottom side. So therefore, in this silicon manufactured technology right now, we cannot expect this three-dimensional description. So we have to consider this is not exactly three-dimensional space, but only one direction along channel direction is allowed it, and for another direction and another direction our system is confined. So maybe some of you are involved with this transport calculation, then now we have to consider the density of state having per electron volt per centimeter, not cubic centimeter or square centimeter. It is because we are considering actually one-dimensional electronic system, not two-dimensional or three-dimensional electronic system. Okay, so then how can we rigorously consider this one? If you wanted to consider then one-dimensional system, then you must start from your one-dimensional system. Once you say that your K-space is one-dimensional, then your density of state will automatically have the scale of this one, because the relationship between density of state and K-space just follows the same line. So instead of considering three-dimensional K-space, if you consider one-dimensional K-space, you will automatically get this one. Okay, but right now this is just a textbook lecture, so we will consider density of state having the unit like this. But once again, I wanted to say that density of state is frequently regarded as energy density. Yes, it is energy density, but it has also another normalization factor corresponding to the dimensionality of your system. Which dimensionality? That is related with the freedom of your electronic movement. So the number 3 shown here is corresponding to the three-dimensional nature of our bulk system. Okay, so now once you have this one, then let's say that what you have is just E of K. Then how can you calculate your density of states? So simply you have all K value and corresponding energy value, say that just count the number of your K points. Okay, this one is corresponding to our desired K space. Then you just add it up to your bins. So once you have EK diagram or EK relation, then immediately you can calculate the density of state. So the reason why I have introduced this arrow means that this is the EK relationship, and once you have EK relationship, you can immediately calculate the density of state out of it, just taking the number of your states corresponding to certain energy range. And another one is, another short note is, although Professor Tower used the notation like capital N for denoting the density of state, but I wanted to say that more frequently used notation for this density of state is D. But in this lecture, I wanted to strictly follow or closely follow his notation. That's the reason why I'm using number N or symbol N, but yes, the D is more preferred one. Okay, so now I hope that all of you understand the concept of density of states, but why don't we just apply our understanding on the ellipsoidal belly? So it is because this is most important one to all of us. Once we can understand this one, now just to multiplying number 6 and multiplying number 2, then we can eventually calculate the density inside our conduction band. Why we have to multiply number 6? This is degeneracy involved with 6 different bellies. This is sometimes called as belly degeneracy. We have 6 different minimums in our silicon conduction band, so we must multiply this one. And how about this number 2, additional multiplication factor 2? This is corresponding to our spin degeneracy. Spin means that we can have up spin and down spin, but up to now we have not considered any kind of consideration about spin up and spin down, and they are degenerate. So we can multiply number 2 to finally is the all available states in our silicon conduction band. Okay, so please note that I will not consider this spin degeneracy and belly degeneracy in this derivation. However, finally you have to multiply these 2 factors, so you have to consider these 2 factors. Number 2 is corresponding to the spin degeneracy, and symbol G is corresponding to the belly degeneracy. Okay, then now let's try to calculate the density of state in ellipsoidal belly. Of course, what I want to say is this is just analytic approach, and if we have really this calculation, this kind of thing cannot be obtained from our simple analytic approach. This is only for where we are talking about. We are just talking about certain concepts only valid nearby this point. So since we are working only with this point, so our derivation is valid only at this point. Are you with me? So although now using the computer simulation we can calculate all kinds of information over several electron volts, but actually that is not that much important to us. To us, most important one is just small energy range over our EC value, because that determines actually most of electronic behavior. There is almost no chance for our electron occupy this point or that point, simply because that is too high energy and its probability to occupy that state is extremely low. So we are considering only this part. Okay, then now everybody understand, calculation of density of state is nothing but just calculating the volume inside our K-space. Once we calculate the volume inside the K-space, and that is multiplied by some factors like some factors like real space volume divided by 2 pi or 2 pi cube of 2 pi, then that will give you the density of state. So simply speaking, we have to calculate the volume of our belly within energy range between E and E plus DE. Now think about this one. Let's say that there is a certain E value. Then what will happen? Once we have E value, then we can have yes, now let's say that this is your iso energy surface corresponding to your E value, let's say. Then energy E, instead of this energy E, now we consider E plus DE, slightly higher energy. Then what will happen? Since we have parabolic behavior of our EK relation, since we have higher energy, we can expect that in a K space, the K values will be also slightly become larger. So instead of this ellipsoid, we can expect another ellipsoid. However, it is just covering this original ellipsoid. You know, this ellipsoid is corresponding to an iso energy surface of E plus DE, and the original one, let's say the red colored one, that is corresponding. Maybe my red color. Okay, my red colored one is corresponding to energy level E. So then what is the volume between energy level E and energy level E plus DE? So you can just calculate the volume of this thin shell obtained by smaller ellipsoid and larger ellipsoid. So you can calculate this volume. And simply speaking, the volume of how can I say, this volume of ellipsoid is not that easy, but you can find that using certain how can I say, certain effective mass. I'm start written here, and using this notation you can find that this is the expression for your volume. How can you do that? So please, this is one of your exercise, so please try to calculate it. But now instead of explaining everything, but let's say that we are now just considering one single belly, not ellipsoidal but just a spherical belly. let's say that there is a spherical belly and whose effective mass is simply given by m star. Then we can find a calculation like two different spheres and shell obtained from two different spheres, and you can easily find that this is the volume of your shell. So now once you have this shell, then what is the difference between this and that? Okay, this is just volume corresponding to your E. However, this is the volume in a range of E and E plus dE. You can easily find that this is 1.5, its power is 1.5, and here you have 0.5. It is because we just consider infinitesimal volume obtained from this range, and from this shell volume, then you can introduce this expression. How can you do that? Just to introduce something like 2 pi over something. Okay, so here we have mxx, myy, and mzz, but you know that in our silicon conduction band, one of them is longitudinal mass, and one of them is transversal mass, and one of them transversal mass. So if we have this kind of configuration, where can you find it? This one can be found when you have a gamma and x point, and this x point is corresponding to, for example, 1, 0, 0 direction. Okay, so 1, 1, 1, and 2 pi over a, you can find this kind of configuration. For example, if you have another one like mt, your mx is transversal mass and your my is longitudinal mass, then it can be found in, not in this point, but in this point, nearby this point. So now you have different values. Now you have your first homework. Of course, no, there is no actual contribution to your grade, but this one is important to understand your concept. So please consider this homework seriously. I wanted to introduce one concept called as a non-parabolicity. Usually we treat energy as a function of k, and it has usually have this square expression, parabolic one. Yes, however, when we consider so-called non-parabolicity alpha, then we say that instead of this e, it has e plus 1 plus alpha e. So you know this one typically have the values like 0.1 per electron volt, something like that. But anyway, this has additional numbers like just per electron volt. What is it? What is its numeric value? It really depends on the situation. It has like this. So alpha times the energy, it yields a certain positive number. So therefore, if we draw certain things like kx and energy axis, if we have sorry about that. Anyway, this one is usual our parabolic expression. However, if we introduce this non-parabolicity, then what will happen? If we go to higher energy, then actually this alpha times E becomes comparable to this number 1, and we can expect an approximate form like alpha times square E equal to 2mk k square. When that happens, when alpha E is much larger than number 1. So now we can neglect the original 1. So you know that now square of energy just follows square of k. So what is it? They have the linearity. So when you draw it, so simply speaking, when you consider non-parabolicity for low energy, it just follows the same behavior, because in this case actually this alpha E does not contribute to anything because this one is a second order thing. However, if we go to high energy, then now it just looks like this. You know that here. Wow. So sorry about that. My drawing is really ugly. But anyway, although my drawing itself is ugly, but please note that once we introduce non-parabolicity, then our EK diagram is deviating from the conventional non-parabolicity at higher energy level. Is this important or not? So to some guys, it's not that important if they are really working on the very first order calculation. However, in reality, actually, even in the case of a silicon conduction band, this non-parabolicity is not, unfortunately, negligible. This one has a serious impact on actually your transport, and when you perform certain calculation with this non-parabolicity and without non-parabolicity, that is considerable, noticeable difference between two calculations. So that's the reason why this is practically important. So that's the reason why I wanted to ask you, please try to calculate the impact of your non-parabolicity factor. So you don't have to anisotropy. You can say that this one k square is just simply given by kx square, ky square, and kz square. It's okay. Don't worry about the anisotropy. Your system is really spherical. However, using this non-parabolicity, please try to calculate the group velocity and inverse mass. Of course, it doesn't have any off-diagonal component, only it has a diagonal component, but please try to calculate, and also density of states. So you will find that by introducing small difference alpha, then your expression will be modified significantly. So that will be quite interesting. So please, once again, homework itself is not contributing to your final grade, but I think that performing this homework is quite important to enhance your understanding. Okay, so then now let's go to the next topic, the second topic in today's lecture. The first topic was, yes, density of states, and now we are going to the calculation of electron density and hole density, and everybody inside this room also understand, in order to calculate the electron density or hole density at equilibrium, we must consider both of density of state and Fermi-Dirac distribution function. So maybe you know that something like this, density of state. So in Tauer's book, it written as n, but anyway, this is the density of state, and Fermi-Dirac distribution, and integrated over certain energy range that is corresponding to our electron density n or p. That is, I assume that at least all of you understand this expression. But my point is, how can we derive this expression from more rigorous way? So starting from our K-space description. So let me just do it together with you. So now you may understand, in this course I wanted to deliver you to way of thinking in the discrete K-space. Many expressions you are seeing in the textbook is just obtained from first consider discrete K-space and later just to convert the summation into integration. That is important message I want to deliver. For example, now let's assume that we wanted to calculate the number of electrons. So conduction band, not in the valence band, only consider conduction band, and how many electrons are there. That can be just obtained by this simple manipulation. So just add 1 if your K-space, K-state is occupied. So you may have, for example, you may have this kind of a thing, empty, occupied. So you may say that 0, 0, 0, and you may have also 2 pi Lx 0, 0, 2 pi Lx times 2, 0, 0. You may have a list of available states in your discrete K space, and you may also have some numbers. Yes, it is occupied. Yes, it is occupied. Unfortunately, this is not occupied. And another one, 0 or 1. You can make a long table for occupancy of your electronic state. Then, if you have this kind of a table, then what you can do is just to consider only occupied K-space. Yes, since you are occupied, add number 1. Since you are occupied, add number 1. Since you are not occupied, you don't contribute. This is the simple counting problem. However, so now let's go to the next step. Instead of this summation only over all occupied K-space, I wanted to perform all K-space regardless whether it is occupied or empty. Then how can we make this transition from restricted summation over occupied state, and now we wanted to the general summation over all available K-states. In order to make it equivalent to the previous one, we introduce one function called as occupancy or something. Anyway, let's say that f. This f is 0 when the state is empty, and this is 1 when it is occupied. Then, although we are learning over all available states, however, if the state is empty, then this f function becomes just 0 and do not contribute anything to our number counting. Oh, okay. Then now previously we should be clever enough to eliminate our state, whether that is occupied or not. but in this rightmost expression, we don't care about that. Just learn over all available states and all kinds of physical consideration is now done by our f. F just to specify whether that is occupied or not and contributed to our summation or not. So now once you understand this one, once you accept this can be a way to calculate the total number of electrons, then transition from just summation into integration is now well known to us. How can you do that? This summation can be just converted into integration. However, we must introduce a certain normalization factor because this is corresponding to an inverse of unit volume in the K space. So now everybody now understand. Sorry. Can you? I made mistakes. So what I wanted to do was not this one, but just highlight. Oh, so sorry about that. But anyway, here we have k of f of k, and here we have f of k. What we do is just to convert our summation into integration. So that's it. So now let's go to the last equation in our slide here. Yes. So generally speaking, when you wanted to evaluate the electron density, the number of electrons in the conduction band should be evaluated from this calculation. So this calculation simply means that first of all, you have to prepare this f function everywhere in your K space and just to integrate it over entire K space. Of course, here entire K space means that the K space of our silicon conduction band, not in valence band. If we perform this kind of integration for K space for our valence band, then that will give us actually the quantity related with the whole density. But right now we are doing the integration only in the conduction band. This is the general form we have to consider. I mean that, is this really related with any kind of energy variable? Actually not. It is written in terms of your K space value. Everywhere related quantity is K space, but yes, that is good, but we wanted to have a more simplified version. Okay, now we have only 2 minutes. I will wrap up today's lecture very soon. So it means that once we know the f function, the physical meaning of f function is quite easy. When we have a certain k value corresponding to an electronic state, and we are asking ourselves whether it is occupied or not. Once we know this quantity, then we can calculate the electron density quite easily, and it is called as distribution function. And say that unfortunately distribution function itself is not a function of energy. It is a function of K. For a given electronic state, we can say that whether that is occupied or if that is 0.5, it has some probability half filled and half empty. However, we cannot, in general case, we cannot say f is in general function of f. It is not possible. I wanted to show you a counter example. One counter example. Here you have a very beautiful graphs. The red color means that higher distribution function corresponding to almost close to 1. And blue one shows small distribution function corresponding to almost 0. And where do you find the origin of this K-space? This is the origin of your space, your K-space. So your isosurface, energy isosurface is given by this circles sharing the same origin. They are corresponding to isosurface. And can you see it clearly? This distribution, in general case, distribution function is not following the iso energy surface. Although, for example, this and that, or that point, although they have the same energy, but depending on the K space direction, you know, this one and this one have the same energy, however their K value have the opposite direction, and in this case it is quite close to number 1, and in this case it is quite close to number 0. In general, we can say that distribution function is a function of K, not E, but a special case. In a special case, sometimes we can assume that although distribution function in general is a function of K, not E, but sometimes we can assume f of E. So in the next lecture, we will talk about what happens if we can assume that distribution function is not a function of general K, but energy variable. Okay, now let's wrap up today's lecture. Bye.